Okay, so one more example for class 17 where we're going to cover drag, and the purpose behind this one is I want to try to show what is dubbed superposition when it comes to drag. That is that you can use a bunch of different drag forces from the various shapes that are happening onto something to get the total amount of drag that would be on the object, right? So we're combining them together. As long as they're not like in front of each other, this will work. So I'm going to give a shout out to my good friend um, Sean Munnis, formerly of the U.S. Coast Guard Academy, who wrote this silliness up here, right? I didn't write this, but he wrote it. My main man, Wade, opened a burger joint, Dopest Burgers in New London, right? So I did not write that. His sign consists of 3 cylindrical supports and signposts, and an elliptical flat plate sign is attached. And he wanted to estimate the drag on the structure when a 50-mile-per-hour wind blows against it. So with that wind at 50 miles per hour, we could take the 5,280 and divide it by the 3,600, and that's, I say, feet per mile and seconds per hour. And so we can convert the 50 miles per hour into feet per second. That's a good starting place. We'll also, once again, use US or British gravitational units. So we're going to say that we're going to use 2.38 e to the minus 3 slugs per cubic foot. And now I'm going to number this just to keep track of things. I'm going to call the ellipse number 1. This is going to be number 2. This is number 3. And this is number 4. And what I can do is I can find the drag force by the total drag by taking now the v squared time, okay, let's go rho v squared. Maybe 1 second, let me go 1/2 rho v squared times the summation of all the CDs and areas right there, right? So I can add all these up and multiply by here, and I should get what the total drag force is. So I say for section 1, we use an oval. And if we go back to what our ovals look like in our drag stuff, we could use the proportional ones right here, right? So for this one, we said it's 5 feet by 16 feet. So that's going to be the L over D of 16 by 5, right? Because it's the long over the short of the thing, right? Is that true? Also, actually, tell you the truth, wait a minute, we don't need to do that. I'm sorry about that. This curve right here is actually for the flat plate to the flow. And so it doesn't really quite matter when you have these proportions, right? This L and this D, because notice that's the flow coming out from the side. Yeah, so the one to use is actually going to be that what we decided is going to be 1.9, right? So I'm sorry about that. So CD1 is approximately 1.9. And the area 1 is going to be equal to, okay, so we might have to look this up somewhere to get the area of an ellipse, but I did it for you. And it's going to be pi over 4, and it's going to be length times width right there, right? So it's going to be 16 times 5. So we end up with an area of 62.82 square feet. And now for 2 here, we're going to have a cylinder. And for a cylinder, we're going to have to look up and approximate what its Reynolds number is. So we have to find its Reynolds number because it has some sensitivity to it. So we're going to go for the smooth cylinder and look those up. So for 2, we're going to have, well, first off, I'll do the area first. That's just going to be the profile area, right? So it's going to be actually that 0.6 times 15, or 9 square feet. And then we look up for the Reynolds number of this. We're going to have U times D times mu. Excuse me, that's a nu, not a mu. So that's 73.33. And the diameter is 0.6. And we're going to divide by this kinematic viscosity, which is for air 1.57 E minus 4. And so what we end up finding is that we have 280,200. And that's going to be 10 raised to the 5.45. And I decided that that's actually going to be in the, I have that down as equal to 0.8. Let me double check where I got that from. Now that I'm looking at the thing. Oh, okay, I can see that. Here's a zoom in. Let me go to this other zoom. That might be better. So this is a cylinder, right? I said it was a smooth cylinder, and we are at 5.45. So here is 5, and halfway down, or thereabouts, is going to be like right here. Or maybe even, actually here's 5 and here's 6. So about halfway down, that's where I decided that's going to be 0.8. So that's how I based my 0.8 on. So I'm going to say my CD2 is approximately 0.8. Your mileage may vary depending on how you read that graph. Let's go to the section at 3. So the area at 3 is going to be 0.8 times 15. So that's going to be 12 square feet. It's RE3. I went ahead and just plugged, the only difference really is going to be that 0.8 right in there, which turns out to be 373, 300, which is going to be 10 to the 5.57. And I decided that CD3 was approximately, let's take it at 5.57. I think it's going to make a pretty big difference here, 5.57. So yeah, it's dropped down quite a bit right in there. I said that it's actually right there at I call that 0.4 right in here. And then for section 4 here, we're going to have a 1 foot by 15. So that's going to be area 4 is 1 foot by 15. So I can do that math, 15 square feet. And our Reynolds number at 4 is going to be equal to 466,700, which is going to be equal to 10 to the 5.67. So there's a lot of movement going on right around that zone. That's almost like right there at the bottom, I think. And I decided that that must be, I came up with a 0.25, right? So that's right there near the bottom of this piece. So you go, CD4 is approximately 0.25. So it's right in the zone where you have the drop. So we take this drag force, and of course we're using the equation up above. So we'll say it's 1/2 the density of 2.38 E minus 3 times the 73.33 squared. And then we multiply all the areas times the drag coefficients. So we had an area of 62.82 times the drag coefficient of 1.9. And I guess I flipped those around, but that's all right. We're going to have 9 square feet times our 0.8. And then we're going to have 12 square feet times 0.4. And then we're going to have our 15 square feet times 0.25. And we're going to have a total drag. It's a total drag, man, of 864.7 pounds. Not nearly as bad as that movie screen, though, huh? That's a pretty bad one. But we could also have, by the way, done these individually, and maybe here's the sign at the top and the thing coming back down, and look at this. And we could have figured out what the individual forces were going to be, so that we could figure out what the moment would need to be here at the bottom, and then do something similar as I did in the 2 examples ago, where I tried to figure out what kind of structure would need to be made to be able to support that. And in this case, I'd probably pick like a hollow cylinder, right? Instead of, before I picked like channel bar, thinking that would be a good bet. But I had a hard time finding one with that section modulus. But we could find a sectional modulus working backwards if we knew what the material was, the strength of the material, and what maybe code safety factor was needed to be used. And if you were down in Florida, they would probably have a higher required safety factor because of hurricane problems. But anyway, that was the another example in drag. I kind of wish I'd done a terminal velocity one, but I did the baseball one, which I thought was kind of cool. So we're going to do some more problems in class 18. We're going to cover lift. So I'm going to start doing the class prep for that one. Exciting. Here at 9 o'clock at night at the University of